Hi, my name is Solomon, and today I will walk you through an in-depth look at the LoCoBot navigation stack. There are two main components when it comes to the navigation stack. One is SLAM, or Simultaneous Localization and Mapping, and the second one is Navigation. So when it comes to SLAM, that's all about creating a map of the environment and localizing the robot within the map. For navigation, that's when the program uses the map and pose information from the robot to move a robot from A to B. It also uses sensor feedback to avoid obstacles in real time. To actually implement this on a robot, there are various ROS packages that can be used. Some are called Gmapping, AMCL, which is for localization only, Google Cartographer, or Hector Mapping. So when it came to choosing which ROS package I would use, there are a few things that I was looking for. First, I wanted the ROS package to be available on many ROS distros. So the one I actually ended up choosing, it works on Kinetic, Melodic, and Noetic, which is great. I wanted it to be actively maintained, which you can literally just find out if people are making commits to the GitHub repository. If there's lots of documentation about it, that's also a good consideration to think about. And then one I ended up choosing, which is called RTabMap ROS. It had another couple features, besides for the ones I just mentioned. Like you could create a point cloud representation of your environment, which is pretty cool just to be able to see that. RTabMap ROS is also pretty nice because it can integrate many types of sensors, such as wheel odometry, or 2D or 3D LiDAR source, or a color depth camera. But some other ROS packages, maybe they're not going to work with all ROS distros, or maybe they only work with a LiDAR or 2D laser scanner, but not with other sensors. AMCL, for example, it's only used for localization. It can't do, it's not used for SLAM, it's just used for localization. So that's pretty much the considerations I had when it came to choosing what SLAM package to use, and that's how I ended up with RTabMap ROS. As far as the navigation part, I decided to go through with MoveBase, mostly because that is the go-to navigation package for ROS 1 for navigation. It's also used in a lot of platforms, such as the Turtlebot 2 platform. It's used there. So, you know, there's a lot of people who use it. People ask questions about it, so you can do a lot of research with it. So that's why I chose that for navigation. All right, in the next part of this tutorial, I'm just going to walk through the main launch file used to start up the navigation stack on the LoCoBot, and also talk about the architecture for how navigation works. So on the left here, I have my launch file. It's located in the Interbotix ROS rovers, Interbotix ROS XS LoCoBots, Interbotix XS LoCoBot nav /launch /XS LoCoBot nav.launch file. So you can see it over there. And I'm just going to bring up the RTabMap documentation here. This is a tutorial you can find if you just search for RTabMap ROS in Google. You'll find a ROS wiki on it, and just go to tutorials, and then there's one called Setup on Your Robot, which is what I ended up following to get this started. Okay, so I told you before already that this ROS package is very flexible, that you can have lots of different sensory inputs. So if you notice on the left here, I have in the very beginning here, two different conditions. If you're using a LiDAR, then you're going to set all these parameters. And if you're not using a LiDAR, then you're going to set all these parameters. And the reason for that is because the LoCoBot that we're selling, you can either get it with a LiDAR and a depth camera, or you can get it just with the depth camera. So the launch file is able to be flexible enough to allow you to choose whichever one you want. Now on the right hand here, let's see the case of what the architecture looks like if you're using a color depth camera. In our case, we're using the RealSense D435. Odometry, we're using the odometry, the wheel odometry from the that is given by the Kabuki Node ROS package for the Kabuki base. And we're also using we're going to go first with the case if you're using a 2D laser scanner, which we are, the A2M8 RPLidar. So this graphic over here is how I ended up organizing my code. So instead of using a Kinect like they're using here, like I said, I'm using a RealSense camera, but it's the same concept. So what it tells you to do is you want to take the color image, the RGB image, as well as the info for the RGB image, and the you want to get the depth. You want to take the depth image data as well, and you want to merge that all together into one single data type called rtabmap/RGBD image. All this does is it condenses all three of those topics into all three of the information from all three of those topics into just one topic, and it allows you to synchronize all that data into one. Besides for the data coming from the color depth camera, we also have laser scan data being fed in to the rtabmap node, and we also have wheel odometry being fed into the rtabmap node. And the rtabmap node has parameters that allows you to specify like which topics you want to use for the odometry and for the laser scan. So it's very flexible like that. And then the rtabmap node takes all that information and it outputs an occupancy grid, which you can visualize in RViz. That just tells you where all the obstacles are in the map. Yeah, and then you can visualize that in RViz, like I said, or you can use rtabmap's proprietary visualizer tool called rtabmap Viz. All right, so that's the case for if you have these three sensory sources. And they have a snippet of a launch file that you can follow to set up your own robot. And if you take a look, they have these parameters I showed you, like these parameters here. This was a good starting point for me when it came to fine-tuning these parameters that you can see on the left here. All right, so that's the case for all three of those sensors, but let's say you don't have that 2D laser scanner. So then if you scroll down a bit, you'll find one that says Connect plus odometry, or in our case, it's going to be a RealSense depth camera with odometry. So it's essentially the same setup where you're merging color image data and depth data into one topic called RGBD image. And you're also feeding in the wheel odometry into the rtabmap node. The only thing missing here is just the laser scanner part. But everything else is the same. You're still going to get the occupancy grid outputted, and you'll be able to do navigation that way. There's a snippet here also with the different parameters you can tune, and that was a good starting point for me as well for fine-tuning those parameters on the left here. Okay. So I've been mentioning these parameters, but like there's so many parameters, how do you know like what each of them do? And that is a great question. And actually, there is a way to find that out. And that is in the advanced parameter tuning site. So if you go here, so there's rtabmap ROS /tutorials/advanced parameter tuning. You can scroll down a bit and it shows you that you can run these commands to learn more about a certain parameter. So let's open up a terminal, press Ctrl-Alt-T. All right, and let us run this command. This assumes, by the way, that you have rtabmap ROS already installed on your computer. Because if you don't, this is not going to work. So ROS run rtabmap ROS. I think I have an extra space there. Hold on. rtabmap params. Let's just put this in full screen. It's going to be pretty big. So you can see here there's a list of all the different parameters and descriptions for them. So this can kind of be a little bit of a lot to look through. So there's a simpler command you can run if you want to look at a specific parameter. And what you can do there is if you press the up arrow key, you can see what the previous command was in the terminal. So what you can do is use a pipe command with grep. And let's say you wanted to look at what this parameter does. So we can copy this and just stick it here and press enter. So we can see here, this param, and it says when a new node is added to the graph, the transformation of its neighbor link to the previous node is refined using registration approach selected. Okay. And you can look at different ways to say parameters or learn more about parameters in this this tutorial here called Advanced Parameter Tuning. Okay. So let's move on. Going down in the launch file, what we're doing here in this next command is we're launching the main driver node. So let me just expand this for a second. Okay, so we launch the XS LoCoBot control.launch file, and what this launch file does is it launches the LiDAR node if there is one. It launches the camera if there is one. Actually, there is always one, so it's always gonna launch the camera. It's also gonna launch the base, and yeah, the Dynamixels will also automatically be launched as well. Okay, so after we launch the individual ROS drivers for the different components of the robot, we go to this section of the launch file here that's all about these nodelets. So let's take a look at these nodelets and see what they do. So the first nodelet we're going to look at is called rtabmapros/rgbdsync. So if you remember before, over here, this nodelet is represented here. It's the nodelet responsible for taking these different topics, the topic for the RGB image, the depth image, and the camera info topic, and just merging it all into one. So that's what that node does. Okay. And after it outputs that RGBD image is used by the nodelet below, this one, and the main rtabmap node to do SLAM or localization. So the rtabmap node itself has a way to take that RGBD image and create its own point cloud from that. All right, so moving down, we have this rtabmap ROS point cloud XYZ RGB nodelet. And what that does is it takes in RGBD images, decimates them, which is a way of filtering them to reduce noise and processing requirements, because the fewer pixels you have to process, then the more efficient the nodelet can run. And then it outputs an actual point cloud 2 message to this nodelet here. So it's taking in this custom RGBD message and is outputting a more generic point cloud 2 message. So what's that going to be used for? It's used by the nodelet after that, called obstacles detection over here. And it takes in point cloud 2 messages and filters out the part of the point cloud data that represents the ground. And there's a very good reason for that. So move base, which is what I said the ROS package we are using for navigation is. So it has different configurations that allow you to tell it, where all the, what it tells you different, you can input topics for different sensors that it can use to do obstacle detection. So in our cases, if you have a LiDAR equipped, you can use the LiDAR to do obstacle detection. And you can also use the depth camera to do obstacle detection. The problem is, if I did not filter out the ground using this nodelet, then even the ground would be considered an obstacle. And essentially the robot wouldn't be able to move because, to use the phrase, the floor is lava type of thing. So that's why you want to filter out the ground. So that's the last nodelet that our tab map that we're using from our tab map ROS. And then we have the main R tab map node here on the left, which does all the SLAM that we were talking about. If you want, you can launch R tab map viz. I would recommend never really doing that. RViz does the same thing, and it allows you to see other types of displays like the raw images from the camera. You can see a representation of the robot. So I'd always recommend just going straight with RViz and using the custom plugin display for our tab map ROS to visualize the point cloud of your environment. Yeah. Okay. Let's just look here to see if I forgot anything. All right. So the next thing that we're going to talk about is move base. So after we do SLAM, then we have this node here, which is responsible for the actual navigation. So let's talk about how that works. So we have different configuration files depending on if the 2D laser scanner is being used or if it's not being used. This is all very standard stuff in the navigation stack. So we have local Costmap params and global Costmap params, common Costmap params. We have planner, a local planner param, global planner params, and a move base params YAML file. So let's look into that. And we can see that over here, this directory is located over here in the config directory. And it has all these YAML files that I just mentioned over here. All right, so going into the common Costmap params YAML file, let's look at it. So it describes all of this stuff. So first parameter we have is called robot radius. This allows you to tell MoveIt how big your robot is. And since we're using a circular robot, we specify that by specifying its radius, in this case at 0.2 meters. The actual, so that would imply that the diameter of the Kabuki base is about 0.4 meters. Truth is, it's a little bit under that, but just to be safe, make it a little bit larger. Then we have these layers here. And in order to understand what that is, you have to understand what a Costmap 2D is. That's a ROS package. So if you look here, I'm in the ROS wiki page for the Costmap 2D ROS package. MoveBase uses this. And this is what, when you see that, the blue and red marks in RViz that are describing obstacles, that's created by this cost map stuff. So a cost map 2D is essentially assigning a cost to every single part of a map, where the higher the cost means the higher the likelihood of there being an obstacle there. The lower the cost means it's more of a free space type of thing. Okay, so something you should know is that there are different layers for that you can create for this cost map. You can have a static map layer. So this is, after you finish mapping out your environment, you essentially have this raw map data. Okay. And that's static. It's not going to be updated ever again. It's going to stay the same. And that's, like the black color is where there's going to be obstacles, and gray is free space. That's no obstacles. That's pretty much what the static map layer represents. And that's created by our tab map ROS. Then we have the obstacle layer. So an obstacle layer is what MoveBase uses to figure out where obstacles are in real time. So, what could happen is you map your environment, but then It might change over time, or people will be walking around, or some objects will be in your environment that weren't there originally. So the obstacle layer allows you to specify a sensor source, like a LiDAR or a depth camera, that can be used to detect different, to detect obstacles, essentially. So you can mark where obstacles are. And then if the obstacle goes away, like if it's a person walking, a person isn't going to be standing still the whole time. He'll be walking around doing whatever he's doing. So if the robot, if a person walks out of the range of the sensor, whether it's the camera or the LiDAR, then it can even clear that obstacle from the map to let MoveBase know, like, oh, by the way, this is free space again. So that's the obstacle map layer. Then we have the inflation layer. All that is a layer that inflates the obstacle layer just to play it safe. So let's go back to that config file. So I already told you what the robot radius is. So the laser layer, this is our first obstacle layer that I mentioned to you about. So I'm specifying that, for the obstacle range, only consider obstacles within the first 2.5 meters of the laser. Ray trace range means if the laser can see to its max range, in this case, I think it's 13 meters, then it can clear an obstacle if there's an obstacle there. Max obstacle height. So that means that maybe, a robot is moving around and it encounters a table. So let's say the point cloud of that table is, maybe it's a meter high, right? So, technically that table might be in the way of a robot. So a robot might think that it can't move there. But if the obstacle is above, in this case, 0.7 meters, then anything above 0.7 meters will be treated as irrelevant. So as long as there's no obstacle within 0 to 0.7 meters, then the robot will think that it can go there. Realistically, that just means the robot will go underneath the table. And this parameter can be tuned. I did a more conservative number here. And it also represents the number for our tallest LoCoBot platform, which is the LoCoBot Widow X250 6DoF. But if you don't have a LiDAR, or if you have a smaller LoCoBot platform, you could change this number to be a little bit lower, so that if you have a smaller table, for example, your LoCoBot will be able to travel underneath it. And these other parameters, you can take a look at the Costmap 2D ROS package to see more about them. I'll just talk about a few more of them. We have observation sources here. That's telling the ROS package, like, here's an arbitrary name I'm going to name for what my sensor source is going to be. So in this case, I have RPLidar, but it could be you can have multiple observation sources in the same layer. But in this case, I just have one. And then after you specify that, you have to describe, okay, for this RPLidar sensor, let's specify all this data. So data type means like what is the ROS message type that this sensor source uses. And since we're using a laser scanner, it's going to be a laser scan. What is the topic name for the laser scan for the RPLidar? Do you want it to allow to mark obstacles? Do you want it to allow to clear obstacles? So like, for example, maybe a LiDAR will see a person walking and it can mark it. But if you have clearing set to false, then even if the person walks away, that obstacle will still be marked in the map and won't go away. But if you want to be able to clear it, then you would want to set this to true. Inf is valid is another Costmap 2D parameter, and it just means like if you have infinite, in your laser scan message, it's common to have inf as one of the values, and if that's the case, it should treat the inf value as the maximum range of the scanner. So that's for the laser scan layer. That is one of our obstacle layers. So, in this layer, the laser scanner can mark and clear obstacles detected by itself, essentially. And then we have another obstacle layer that's for just the depth camera, and is very similar to, and these parameters work the same way as for the laser scanner. The only difference is that we're using a point cloud message type, because it's not a laser scanner. It gives you point cloud data, and the point cloud data that we're going to point to is the output from that last nodelet, the last RTMap ROS nodelet that was showing you where the obstacles are. So again, we want the depth camera to be able to mark its own obstacles and to clear its own obstacles. So like what you could theoretically do is, in your observation sources, you could have, maybe just one obstacle layer, and you just call this obstacle layer. And in the observation sources, you could have RPLidar, and you could have, what did I call this? And depth, and then specify both here. But then the issue with that is the LiDAR could theoretically clear any obstacles detected by the depth camera, and vice versa. The depth camera could clear obstacles detected by the LiDAR, and that might not be something you want to do. And just to give you an example, right, so the LiDAR operates on a 2D plane at a certain height above the robot, okay? So let's say the depth camera sees an obstacle that can't be detected by the LiDAR, so it's going to mark it, but then it's automatically going to be cleared by the LiDAR because the LiDAR isn't seeing it. So that's why you want to have them as their own obstacle layers. Okay, and then we have the inflation layer. And this is just how much you want to inflate the obstacle layers by. So here I have an inflation radius of 0.5 meters, and then this cost scaling factor is totally arbitrary. I think it might have been based on the TurtleBot ROS packages that I saw on GitHub. You can also specify parameters for the static layer, but I decided to leave them at their default, so they're not specified here. Okay, so that was the common Costmap params. Now let's go to the global Costmap all params YAML file. So in this case, we're specifying, when it comes to doing navigation, so we have a global planner and we have a local planner. The global planner is used to figure out, based on all of the map data, how to get from where the robot currently is to its destination goal. And there are different layers that are used for that. So first we have the raw map data layer, the static layer I mentioned before. Then we have both the laser and depth layer to detect obstacles in real time. And then we have the inflation layer. So this layer is superimposed on the static layer, and the depth layer is superimposed on the laser layer, and the inflation layer is superimposed on the depth layer. So by the time you add all these layers together, you'll get your final resulting cost map. And these are just some parameters you can look at, and they're defined again in the Costmap 2D ROS package. You can see them there. Just how often should the cost map be updated? Once a second. The frequency should be 0.5 second. So you can see those parameters in the Costmap 2D section. All right. So that's assuming you're using both a LiDAR and a depth camera, but if you're just using the depth camera because you don't have a LiDAR, then you just take out the laser layer in this case. That's the only difference here. Let's look at the local cost map. So in the local cost map case, we're not going to use the static layer. We just want to focus on where the robot currently is. And in this case, we're specifying a 4 meter by 4 meter square around where the robot is at the center of that square of where we want to generate the cost map. And we're basing it mostly on just the sensor data for detecting obstacles and the inflation layer. And then the local cost map depth params, that's assuming it's the same as this all params YAML file, except it doesn't include the laser layer since that doesn't exist. So once we're done with the configuring the cost maps for both the local cost map and global cost map, then we can talk about planners. So what the global planner does is it it uses the global Costmap to figure out how to get the robot from where it currently is to its goal pose. And in here, we're defining our global planner. It's the nav FN ROS planner. Well, we actually don't define the planner here. We're setting a configuration parameter specifically for this this global planner called allow unknown. I do not recall what that parameter does, but you can search for it. If you go to the nav FN ROS package, let's just type that in really quick. So it should have a list of what that parameter does. Specifies whether or not to allow nav FN to create plans that traverse unknown space. Okay, so let's say what that means is, let's say you do SLAM, and then after you finish doing SLAM, you stop your mapping, and now you just want to localize the robot within the map. So you're just doing localization, no more mapping. So allow unknown is, do you want the robot to travel in unknown space? It was not mapped out yet. By default is true, but just to be safe, you might want to say you want to set that to false. If you want to keep the robot in a specific environment, you don't want it traveling out of that environment. So that's what that does. Then we have local planner params. So this is the local planner. It's the default local planner normally used by move base, just like the nav FN ROS is the typical global planner used by move base. So I just decided to keep with that. And you can see more about what these parameters mean just by looking at the trajectory planner ROS on the ROS wiki and looking at the parameters. Okay, mostly it's just for optimizing, you know, the local plan. The local plan is right. So let me back up a bit. So we have the global plan, right? And that's you set a goal pose. You want the robot to go from where it currently is to its desired destination, but let's say that's, you know, 11 meters away, right? That global plan also doesn't incorporate dynamic obstacles, okay? So let's say the robot is moving and then it detects a obstacle that's not there that wasn't, you know, planned for in the global plan. So what the local planner will do is figure out a way around that obstacle in an optimal way. So like it doesn't veer off too far from where the global plan is set to go, but it doesn't hit the obstacle either. So that's just like some of the parameters here, specifically like the path distance bias and the goal distance bias. Okay. Then we have the move base params. So I just want to point out two of the params here, and that is the base local planner. So this is where you actually define which local planner you want to use. And in this case, we're using trajectory planner ROS. And then you also specify which global planner you're going to use. And we're specifying in here to be the nav FN ROS global planner. Okay. All right. So that's the move base node. And then the only node after that is this ROS topic node, where we command a specific pan and tilt value for the camera. So the pan is 0 and the tilt is configurable, but it's set to 0.2618 radians. So the angle, so it's a little bit of a tilt pointing down. And the reason I did that is because you want the depth camera to be able to detect obstacles, and if it's staring straight forward, it might not do as good of a job detecting obstacles that are closer to the robot and nearer to the floor. So I just have it pointed down a little bit so that it can detect those obstacles. Anyway, that covers the navigation stack, and I'll see you next time. Thank you.